Carbon capture and storage. A pathway to net zero. Course outline. Introduction to carbon capture and storage. The science of carbon dioxide emissions. History and evolution of CCS. Technologies for carbon capture. Transportation of captured CO. Storage methods and sites. Economic and financial aspects of CCS. Policy and regulatory frameworks. Environmental and social considerations. Conclusion: CCS in the energy transition. Part 1. Introduction to carbon capture and storage. What is carbon capture and storage (CCS)? Carbon capture and storage (CCS) is a suite of technologies designed to reduce greenhouse gas emissions by capturing carbon dioxide (CO) at its source, transporting it, and storing it securely underground. The main goal of CCS is to prevent CO from entering the atmosphere and contributing to global climate change. CCS can be applied to large-scale emission sources such as power plants, industrial facilities, and refineries. Why is CCS important? The growing concentration of CO in the atmosphere, primarily from the burning of fossil fuels, is the leading cause of anthropogenic climate change. Despite the global shift toward renewable energy and energy efficiency, fossil fuels still account for a significant portion of the world's energy supply. CCS provides a transitional solution that allows for continued use of fossil fuels while drastically reducing their environmental impact. Additionally, CCS is one of the few technologies capable of decarbonizing hard-to-abate sectors like cement, steel, and chemical manufacturing. It also plays a critical role in producing low-carbon hydrogen and enabling negative emissions when combined with bioenergy, known as BECCS, bioenergy with carbon capture and storage. How does CCS work? CCS typically involves three main steps. Capture. CO is separated from gases produced in electricity generation and industrial processes. This can be done pre-combustion, post-combustion, or via oxy-fuel combustion. Transport. Once captured, Colorado is compressed and transported usually via pipelines to a storage site. Storage. CO is injected into deep underground rock formations such as depleted oil and gas fields or deep saline aquifers, where it is securely contained for hundreds to thousands of years. Global need for CCS. According to the Intergovernmental Panel on Climate Change, IPCC, and the International Energy Agency, IEA, limiting global warming to 1.5 degrees Celsius or even 2 degrees Celsius requires a portfolio of solutions, including CCS. Projections show that without CCS, the cost of achieving climate targets could be significantly higher. CCS is not a silver bullet, but it is a critical piece of the climate action puzzle. Debunking common myths. There are several misconceptions about CCS. Myth 1: CCS is unproven. Reality: CCS technologies have been in use for decades in the oil and gas industry, particularly for enhanced oil recovery (EOR). Myth 2: CCS is unsafe. Reality: properly selected and managed storage sites can safely contain CO for geological timescales. Monitoring and verification practices ensure integrity. Myth 3: CCS delays the transition to renewables. Reality: CCS complements renewables by decarbonizing sectors that cannot easily switch to clean energy. Structure of this part. This part will explore the technical, economic, environmental, and policy dimensions of CCS. The parts ahead will guide you through the science of emissions, the technology behind capture and storage, case studies of CCS in action, and the future prospects of this vital climate technology. Part 2: The science of carbon dioxide emissions. The carbon cycle and human impact. The carbon cycle is the natural process by which carbon moves through the Earth's atmosphere, oceans, soil, and living organisms. For thousands of years, this cycle maintained a balance, ensuring that the concentration of CO in the atmosphere remained relatively stable. However, human activities, particularly the combustion of fossil fuels, have significantly altered this balance. When coal, oil, and natural gas are burned for energy, they release carbon that has been locked underground for millions of years. This influx of CO exceeds the capacity of natural sinks like forests and oceans to absorb it, leading to an accumulation in the atmosphere. Sources of CO emissions. Carbon dioxide is emitted from a variety of sources, which can broadly be categorized as stationary sources: power plants, coal, natural gas, oil; cement and steel manufacturing facilities; refineries and petrochemical plants; pulp and paper mills; mobile sources: cars, trucks, airplanes, and ships. While CCS is primarily focused on stationary sources due to the concentration and volume of emissions, research into mobile applications is ongoing. CO and climate change. CO is a greenhouse gas (GHG), meaning it traps heat in the Earth's atmosphere. While it is less potent than other GHGs like methane, carbon tetrahydride, or nitrous oxide, dinitrogen monoxide, its abundance and longevity make it the most significant contributor to human-induced global warming. Pre-industrial CO levels were about 280 parts per million, ppm. Today's levels exceed 420 ppm and continue to rise annually. This increase correlates closely with global temperature rise, sea level rise, melting polar ice, and extreme weather events, all symptoms of climate change. The concept of carbon budget. The carbon budget refers to the amount of CO that can be emitted while still having a likely chance of limiting global warming to a specific temperature target, e.g., 1.5 degrees Celsius or 2 degrees Celsius above pre-industrial levels. As of recent estimates, to stay below 1.5 degrees Celsius, the world can emit only about 300 to 500 gigatons of CO more. At the current rate of -40 gigatons per year, the budget will be exhausted within a decade without major interventions. This urgency underpins the need for emission reduction technologies, including CCS, to supplement renewable energy and efficiency measures. Hard-to-abate sectors. Some sectors are especially difficult to decarbonize due to the nature of their industrial processes. Cement, CO, is released both from energy use and the chemical transformation of limestone, calcination. Steel, traditional production involves reducing iron ore with carbon. Chemicals, ammonia, methanol, and hydrogen production are carbon-intensive. In these sectors, CCS offers a practical route to deep emission cuts, making it indispensable for net zero pathways. CO characteristics relevant to CCS. Understanding the physical and chemical properties of CO is essential to its capture, transport, and storage. Colorless and odorless gas at ambient conditions. Heavier than air, allowing it to be stored underground. Compressible into a supercritical state, where it behaves like both a gas and a liquid, ideal for transport and storage. Non-flammable and non-toxic in low concentrations, but dangerous in confined spaces at high concentrations due to asphyxiation risks. These properties make CO suitable for pressurization, injection, and long-term storage in geological formations. Part 3: History and Evolution of CCS. Early ideas and scientific foundations. The foundation of carbon capture and storage, CCS, is rooted in basic principles of chemistry, geology, and engineering. As early as the 1930s, the oil and gas industry recognized the potential of injecting CO into underground reservoirs to enhance oil recovery, a technique now known as enhanced oil recovery (EOR). However, the idea of using geological storage for climate mitigation only gained traction in the latter part of the 20th century. The concept of capturing CO from industrial emissions and storing it underground was proposed in academic literature in the 1970s and 1980s. This idea was initially driven more by concerns about acid rain and air pollution than by climate change. The 1990s, CCS enters the climate dialogue. The 1990s marked a turning point for CCS, as global concern about climate change intensified. The Intergovernmental Panel on Climate Change (IPCC) published its early assessment reports, highlighting the role of CO in global warming. The Kyoto Protocol, 1997, established legally binding targets for developed countries to reduce GHG emissions, creating a policy framework where CCS could gain relevance. Scientists and engineers began seriously evaluating the feasibility of capturing CO from fossil fuel plants and storing it underground to prevent atmospheric release. Landmark CCS projects. Several demonstration projects proved the viability of CCS in the real world. Sleipner Project, Norway, 1996–present, the world's first commercial CCS project, injecting around 1 million ton of CO per year into a saline aquifer beneath the North Sea. Operated by Equinor, Sleipner showed that CO could be stored safely and monitored over long periods. Weyburn Midale CO Project, Canada, 2000, a large-scale EOR and CO storage project that became a case study in monitoring and verification of geological storage. Insular Project, Algeria, 2004–2011, captured CO from natural gas production and stored it in a deep saline formation. Although discontinued, it provided key insights into reservoir behavior and monitoring. These projects demonstrated that CCS was technically possible, even if costs remained a barrier. CCS in policy and technology roadmaps. By the 2000s, CCS began appearing in major climate and energy strategies. The IEA, International Energy Agency, identified CCS as one of the key technologies needed to halve emissions by mid-century. The IPCC's Fourth Assessment Report, 2007, confirmed that CCS could contribute 10 to 20% of global emission reductions. The Global CCS Institute was established in 2009 to promote and coordinate international efforts on CCS research, policy, and deployment. Governments began funding pilot projects and research centers, and private sector interest increased, especially among energy companies seeking ways to reduce their carbon footprints. Setbacks and challenges. Despite the promising start, CCS faced major hurdles. High costs. Building and operating CCS systems was and still is expensive, especially in the absence of a high carbon price or robust policy incentives. Public resistance. Concerns about safety, environmental impacts, and the role of CCS in prolonging fossil fuel use led to opposition in some communities. Regulatory gaps. Many countries lacked clear regulations for CO storage, liability, and long-term site stewardship. These challenges caused delays and cancellations of several high-profile CCS projects during the 2010s. 3.6 renewed momentum in the 2020s. In recent years, CCS has seen a resurgence due to net zero commitments by countries and corporations, which make CCS essential for decarbonizing hard-to-abate sectors. Technological advancements that have reduced the cost of capture and improved storage monitoring. Carbon markets and tax incentives, such as the US 45Q tax credit and the EU Innovation Fund, which improve the economics of CCS. The emergence of carbon removal technologies, such as direct air capture (DAC), and bioenergy with CCS (BECCS), which rely on CCS infrastructure. Global capacity for CO storage is expanding, with dozens of commercial-scale projects planned or underway. Part 4: Technologies for Carbon Capture. Overview of CO capture. Capturing carbon dioxide is the first and most crucial step in the CCS chain. It involves separating CO from gases produced during industrial processes or energy generation. The goal is to isolate CO in a pure pressurized form so it can be transported and stored efficiently. There are three main types of CO capture technologies: post-combustion capture, pre-combustion capture, oxy-fuel combustion. Each method is suited to specific applications and has its own set of advantages and challenges. Post-combustion capture. This is the most widely used and mature technology, especially in retrofitting existing fossil fuel power plants. How it works. CO is captured after the fuel is burned. Flue gas, containing CO, nitrogen, water vapor, and other gases, is treated to separate the CO. Common techniques. Chemical absorption using solvents. Amine-based solvents like monoethanolamine (MAA) absorb CO from flue gas. The CO-rich solvent is then heated to release CO and regenerate the solvent. Membrane separation. Special membranes selectively allow CO to pass through. Adsorption. Solid materials like zeolites or activated carbon adsorb CO, which is later released under pressure or heat. Advantages. Can be retrofitted to existing plants. Commercially proven. Challenges. Energy-intensive regeneration, often called the energy penalty. Solvent degradation and corrosion. Pre-combustion capture. This method is typically used in industrial applications and integrated gasification combined cycle (IGCC) power plants. How it works. Fuel, usually coal or natural gas, is gasified to produce a mixture of hydrogen and carbon monoxide called syngas. The CO is then converted to CO and hydrogen via the water-gas shift reaction. CO is captured, and the hydrogen can be used as a clean fuel. Advantages. Higher CO concentration makes capture more efficient. Lower volume of gas to treat. Challenges. Not easily retrofitted to existing plants. Requires major infrastructure changes. Oxy-fuel combustion. A less common but promising technology. How it works. Fuel is burned in pure oxygen instead of air, resulting in a flue gas that contains mostly CO and water vapor. The water vapor is condensed, leaving nearly pure CO for capture. Advantages. Produces a high-purity CO stream. Simplifies separation. Challenges. Oxygen production is energy-intensive. Requires significant changes to boiler and combustion systems. Emerging and hybrid technologies. Several innovative methods are under development to improve efficiency and lower costs. Calcium looping uses calcium oxide to capture CO through a reversible chemical reaction. Cryogenic separation cools the gas stream to separate CO by freezing. Solid sorbents, metal organic frameworks (MOFs), and other advanced materials that selectively bind CO. Direct air capture (DAC) captures CO directly from the atmosphere using chemical or physical processes, more challenging due to low ambient concentrations but vital for negative emissions. Selecting the right capture technology. Choosing the appropriate capture method depends on several factors. Type of facility, power plant, cement factory, etc. Concentration of CO in exhaust gases. Scale and economics. Regulatory and policy environment. Often, hybrid systems or integrated approaches are employed to optimize cost and performance. Future directions. Research and development are focused on reducing energy requirements, improving solvent stability, scaling up DAC and modular capture units, lowering costs through automation and AI optimization. As policies tighten and carbon markets expand, innovation in capture technologies will be key to accelerating CCS deployment. Part 5. Transportation of captured CO. Why CO transport matters. Once carbon dioxide has been captured from power plants or industrial sources, it must be transported to a designated storage site. Efficient and secure transportation is essential to the overall success and scalability of CCS systems. Without reliable transport infrastructure, even the most advanced capture and storage technologies cannot operate at full potential. Forms of CO for transport. Before transport, captured CO is compressed into a supercritical state, a dense fluid-like form that combines the properties of gases and liquids. This form minimizes volume and improves flow efficiency. Supercritical CO, achieved at temperatures above 31.1 degrees Celsius and pressures above 7.38 megapascals. Advantages: lower transportation cost per unit, easier to inject into geological formations, and safer due to reduced gas expansion risk. Modes of CO transport. Pipelines. The most common and cost-effective method for transporting large volumes of CO over land. Onshore pipelines, typically buried underground for safety and environmental protection. Offshore pipelines, used to reach undersea storage sites like depleted oil fields or saline aquifers. Advantages: proven technology, continuous high-volume transport, lower operating costs over long-term use. Challenges: high capital investment for construction, regulatory hurdles and land use permissions, public acceptance and safety concerns. Road and rail transport, used for small-scale or early-stage projects. Road tank trucks, ideal for pilot projects or remote locations. Rail cars can carry larger volumes than trucks but less flexibility in routing. Limitations: not suitable for large-scale deployment. Higher per-ton transportation costs. Emission footprint from fuel use. Ships. A promising method for transporting CO across long distances or between countries, especially when offshore pipelines are not feasible. Liquefied CO ships operate similarly to LNG carriers. Loading and unloading terminals are required at both ends. Benefits: flexibility in international CCS networks. Potential for regional CO hubs. Barriers: limited current infrastructure. Regulatory and safety standards still developing. Infrastructure and network design. A future with widespread CCS deployment will require a CO transport network, similar to natural gas grids. Hub-and-spoke models, multiple capture sites feed into shared pipelines leading to centralized storage hubs. Integrated CCS corridors, regional infrastructure that connects industrial clusters to common storage basins. Planning such infrastructure requires careful coordination between governments, industries, and communities to ensure efficiency and public trust. Safety and monitoring. CO transport is generally safe and governed by strict regulations, especially in the pipeline industry. Safety considerations include pipeline integrity monitoring, pressure and leak detection systems, emergency response plans, material selection to prevent corrosion from impurities. Historical data from decades of CO use in enhanced oil recovery (EOR) demonstrate a strong track record for pipeline safety. Regulatory framework. Countries with active or planned CCS deployment are developing transport-specific policies including permitting and routing rules, cross-border CO transport agreements, environmental impact assessments, liability and insurance structures. In the European Union, a Trans-European Networks for Energy (TEN-E) initiative supports CO pipeline corridors across member states. In the United States, the 45Q tax credit and proposed CO infrastructure funding aim to expand the national pipeline system. Future outlook. As CCS scales up, Colorado transport will become a major industrial sector in its own right. Innovations are being explored in modular pipeline construction, advanced leak detection with AI and satellites, dynamic CO routing systems, hydrogen-ready pipeline retrofits. Integrated planning of capture, transport and storage is critical to maximize efficiency and cost-effectiveness. Part 6: Storage methods and sites. The goal of CO storage. The ultimate goal of carbon dioxide storage is permanent sequestration, keeping captured CO isolated from the atmosphere for thousands to millions of years. This is achieved by injecting the gas deep underground, into carefully selected geological formations that can safely contain it under natural pressure and temperature conditions. For storage to be effective, the site must have high porosity and permeability to allow CO to spread, and an impermeable caprock to trap it and prevent leakage. Types of geological storage sites. There are three primary types of geological formations suitable for long-term CO storage. Depleted oil and gas reservoirs. These are former hydrocarbon reservoirs that have already held gas or oil for millions of years, proving their natural ability to trap fluids. Advantages. Well understood geology from prior exploration. Existing infrastructure may reduce costs. Potential for enhanced oil recovery (EOR), where CO is injected to extract remaining oil. Challenges. Limited capacity compared to saline aquifers. Potential leakage pathways if old wells are not properly sealed. Deep saline aquifers. These are porous rock formations saturated with salt water and found nearly everywhere underground. Advantages. Vast global storage potential. Not used for drinking water or agriculture. CO reacts with minerals over time to form stable carbonates. Challenges. Less detailed geological data. Higher monitoring and verification costs. Unminable coal seams. CO can be injected into coal seams too deep or poor in quality for mining. The CO bonds with coal and releases methane, which can be captured and used, known as enhanced coalbed methane (ECBM) recovery. Advantages. Dual benefit, storage and methane recovery. Potential economic incentives. Challenges. Lower storage capacity. Risk of gas migration through fractures. Storage mechanisms. CO is held in the subsurface through a combination of physical and geochemical trapping mechanisms. Structural trapping. CO accumulates beneath impermeable rock layers caprock that prevent its escape. Residual trapping. CO gets trapped in the tiny pores of rock as disconnected droplets. Solubility trapping. CO dissolves into the brine present in the formation. Mineral trapping. CO reacts chemically with the surrounding rocks to form stable carbonate minerals, a process that offers permanent storage. Site selection criteria. Choosing a safe and effective storage site involves extensive geological, hydrological, and environmental analysis. Key criteria include depth, usually greater than 800 meters, to maintain CO in a supercritical state. Porosity and permeability for CO, injectivity and distribution. Thick, unbroken caprock to act as a seal. Absence of faults or fractures that could enable leakage. Distance from drinking water sources and population centers. Long-term monitoring capability. Site development and operation. Storage projects follow a sequence of steps. Site characterization, geological surveys, seismic studies, core sampling. Permitting and regulatory approval, compliance with environmental laws. Well drilling and injection infrastructure. CO injection operations, continuous or pulse depending on capacity. Monitoring and verification, groundwater checks, seismic monitoring, satellite imaging. Closure and post-injection care, long-term stewardship, liability transfer. Monitoring and risk management. A well-designed monitoring system ensures that CO stays underground and helps detect any anomalies early. Seismic surveys detect CO movement. Pressure sensors track subsurface behavior. Tracer gases help verify CO origin and integrity. Groundwater sampling ensures no contamination. International standards, such as those from the ISO and IEA GHG program, guide monitoring practices and contingency planning. Examples of storage projects: Sleipner Field, Norway, injecting CO into a saline aquifer beneath the North Sea since 1996. Quest Project, Canada, captures and stores CO from oil sands hydrogen production. Gorgon Project, Australia, one of the largest dedicated storage projects, injecting CO into a deep saline formation. These projects have demonstrated successful, safe and monitored storage over extended periods. The future of CO storage. The potential for geological storage is vast, estimated at trillions of tons of CO globally. Future developments include regional storage hubs, international CO transport and storage agreements, advances in mineralization and in situ conversion, integration with negative emissions technologies like BECCS and DAC. With the right policies, incentives and technological advances, Colorado storage can scale to meet climate targets while safeguarding communities and ecosystems. Part 7. Economic and financial aspects of CCS. The cost structure of CCS. Carbon capture and storage involves three main components: capture, transport and storage, each contributing to the overall cost of the system. Understanding the economics is vital for assessing its viability and competitiveness with other climate mitigation options. Breakdown of typical CCS costs per ton of CO. Capture 60 to 70%. Transport 10 to 20%. Storage and monitoring 10 to 20%. Total costs can range from $50 to $150 per ton of CO, depending on the technology used, location, scale, and whether there are cost-saving factors like existing infrastructure. Factors influencing CCS economics. Several factors affect the economic feasibility of CCS projects. CO concentration in flue gas. Higher concentrations, e.g., from natural gas processing or cement production, reduce capture costs. Scale of the facility. Larger facilities benefit from economies of scale. Proximity to storage sites reduces transportation expenses. Energy penalty. The extra energy required to capture and compress CO can reduce overall plant efficiency. Regulatory frameworks and permitting requirements. Business models for CCS deployment. To date, CCS deployment has relied heavily on public-private partnerships and government support, as market incentives alone have not been sufficient. Common business models include: 1. Government-funded demonstration projects. Early-stage pilots to prove viability. Typically, fully or partially subsidized. 2. Industry-led projects with tax credits. Companies invest when there are favorable incentives, e.g., the US 45Q credit. 3. Carbon pricing-driven investment. Viable where carbon pricing is high enough to justify CCS investment. More effective in regions with carbon markets or emissions trading schemes, ETS. 4. CO utilization and revenue generation. Enhanced oil recovery, EOR. Emerging markets for CO-derived products, concrete fuels, chemicals. 7.4 Policy and financial incentives. Governments play a key role in unlocking CCS investment through targeted policies and financial mechanisms. Carbon pricing. Carbon tax or cap-and-trade systems increase the cost of emitting CO, making CCS more attractive. The EU ETS, Canada's carbon pricing, and California's LCFS are examples. Tax credits. 45Q USA offers up to $85 per ton for CO stored in saline formations and $60 per ton for EOR. Investment tax credits, ITCs, in some regions help offset capital costs. Grants and subsidies. National programs fund research, development and deployment, e.g. UK's Net Zero Innovation Portfolio, Norway's Longship project. Green financing instruments. Green bonds, climate funds, and sustainability-linked loans are increasingly being directed towards CCS projects. Investment risks and barriers. Despite support, investors face several risks in CCS. Policy uncertainty. Changes in regulation or political support can jeopardize projects. Technology risk, especially in newer or less proven capture technologies. Market risk. Uncertainty in carbon prices or demand for CO-derived products. Long-term liability. Who is responsible for storage sites after closure? Mitigating these risks requires clear long-term policies, risk-sharing mechanisms and insurance schemes. Economic benefits of CCS. Beyond climate mitigation, CCS can generate economic returns through job creation in engineering, construction and operations. Revitalization of industrial regions by decarbonizing legacy infrastructure. Increased competitiveness for industries in carbon-constrained markets. Export potential of CCS services, expertise and equipment. Global cost trends and outlook. As CCS technologies mature and scale, costs are expected to decline, much like what has happened with solar and wind energy. Learning by doing and modular system design. Standardization of equipment. Integration with hydrogen DAC and BECCS systems. Digital monitoring and AI for operational efficiency. According to the IEA and Global CCS Institute, achieving net zero emissions globally could require 2 to 6 GT of CO storage per year by 2050, involving trillions in infrastructure investment. This positions CCS as a key opportunity for climate-aligned capital deployment. Part 8. Policy and Regulatory Frameworks. Why policy matters for CCS. Carbon capture and storage, CCS, is a complex and capital-intensive solution that cannot scale without strong government policy, legal clarity and public support. Policies and regulations not only provide incentives and funding, but also set the legal framework for CO handling, transport, and long-term liability. In the absence of robust governance, private investment in CCS remains limited due to high financial and regulatory risks. Key policy goals for CCS. Effective CCS policy frameworks aim to encourage deployment through incentives, mandates, and subsidies. Ensure safety and environmental integrity through regulations and monitoring. Clarify legal and financial responsibilities, especially for long-term storage. Support infrastructure development, e.g., pipeline networks and CO hubs. Foster public trust through transparency, community engagement, and environmental protections. International CCS policies and agreements. Several international frameworks support CCS as a climate solution. The Paris Agreement 2015 recognizes CCS as a legitimate mitigation option. Encourages countries to include CCS in their nationally determined contributions, NDCs. London Protocol 1996 originally restricted CO disposal in marine environments, but has since been amended to allow transboundary CO storage, which is crucial for international CCS networks. Clean Development Mechanism, CDM. CCS was accepted under CDM rules, allowing projects in developing countries to earn carbon credits. IPCC support. The Intergovernmental Panel on Climate Change, IPCC, consistently recognizes CCS as essential for achieving net zero goals, especially for hard-to-abate sectors. National policy approaches. United States offers the 45Q tax credit for CO storage and utilization. Funds R&D and demonstration through the Department of Energy, DOE. Regulates injection wells under the EPA's Class 6 permitting system for geological storage. European Union recognizes CCS under its EU Emissions Trading System (ETS). Supports cross-border infrastructure through the TEN-E regulation. Includes CCS in the Innovation Fund and Net Zero Industry Act. United Kingdom. Committed to developing industrial decarbonization clusters, with CCS at the core. Provides funding through the Carbon Capture and Storage Infrastructure Fund, CCSIF. Set up a business model with a regulated asset base (RAB) approach for transport and storage. Norway. Pioneer in CCS policy, home to the Sleipner and Snøhvit projects. Runs the Longship project, a full-chain CCS system including capture, transport and offshore storage. Supported by robust government subsidies and state-owned company Equinor. Australia. CCS eligible under the Emissions Reduction Fund, EARTH. Hosts the Gorgon project, one of the world's largest CCS facilities. China. Rapidly expanding R&D and pilot projects. CCS is featured in the country's 5-year plans and national CO peaking roadmap. Legal and regulatory challenges. Implementing CCS at scale requires addressing several legal and regulatory concerns. 1. Long-term liability. Who is responsible for stored CO, 50 or 100 years after injection? Some governments, e.g. UK, US, assume long-term liability after site closure under strict conditions. 2. Cross-border CO transport. Legal frameworks must allow international pipelines or shipping routes. This is an emerging legal frontier, with protocols under development. 3. Permitting and environmental review. Lengthy and complex processes can delay projects. Streamlining procedures without compromising safety is a growing priority. 4. Public engagement and consent. Public resistance to CO pipelines and storage near communities can block projects. Transparent consultation, community benefits, and environmental justice are crucial. Role of carbon markets. Cap-and-trade systems, carbon taxes and offset markets can incentivize CCS by making it more economical to capture and store emissions, rather than pay penalties. Allowing companies to trade CO storage as carbon credits. Encouraging investment in negative emissions technologies such as BECCS and direct air capture with storage, DACS. The need for harmonized standards. As CCS scales internationally, there's a growing push for standardized monitoring and verification protocols. Storage site qualification guidelines. Transboundary liability rules. Data sharing and reporting formats. Organizations like the International Organization for Standardization, ISO, and IEA Greenhouse Gas R&D program are leading efforts in this direction. Policy recommendations for accelerated CCS deployment. Establish clear national CCS strategies tied to climate targets. Provide long-term policy certainty through predictable incentives and support. Fund shared infrastructure to lower entry barriers for industries. Create robust legal frameworks for storage liability and cross-border transport. Support public awareness and community participation in CCS decisions. Integrate CCS with industrial decarbonization plans, hydrogen strategies and innovation funds. Part 9. Environmental and social considerations. Introduction. While carbon capture and storage (CCS) holds immense promise for mitigating climate change, it also presents environmental, social, and ethical questions that must be addressed transparently. Public perception, community acceptance, ecosystem impacts, and long-term safety are all critical to the sustainable and responsible deployment of CCS technologies. Environmental benefits of CCS. 1. Climate mitigation. CCS reduces CO emissions from power plants, cement, steel, and other heavy industries. Enables negative emissions when paired with bioenergy, BECCS, or direct air capture, DACS. 2. Cleaner industrial transition. Helps existing industries reduce their carbon footprint without complete overhauls. Supports low-carbon hydrogen and fuels production. 3. Protection of natural ecosystems. By slowing climate change, CCS helps protect biodiversity, agriculture, and water systems from climate stress. Potential environmental risks. Despite the benefits, CCS projects must mitigate and manage several risks. 1. Groundwater contamination. Improper CO injection or storage could displace or contaminate underground water sources. Requires careful site characterization and well integrity management. 2. Induced seismicity. CO injection can change subsurface pressure and trigger microearthquakes. Risk is generally low and managed with pressure control and seismic monitoring. 3. CO leakage. While rare, potential leakage could occur through faults, fractures, or old wells. Could reduce the climate benefit and pose safety or ecological risks. 4. Energy penalty and emissions. CCS increases energy use at facilities known as parasitic load, potentially increasing local air pollution if powered by fossil fuels. The source of energy used in capture processes is critical to overall climate benefit. Social and community considerations. 1. Public perception and trust. Many communities are wary of CCS due to unfamiliarity or association with fossil fuels. Transparent communication and early community engagement are essential for trust building. 2. Environmental justice. CCS projects should not disproportionately impact vulnerable or marginalized communities. Location of pipelines, injection sites, and infrastructure must consider equity and inclusion. 3. Land use and livelihoods. Land used for storage facilities or infrastructure may impact agriculture or traditional land users. Consultation with indigenous peoples, farmers, and local residents is crucial. 4. Community benefits. Local job creation, infrastructure investment, and skills training can enhance support. Sharing economic gains through community benefit agreements can align interests. Regulatory safeguards and best practices. Responsible CCS projects integrate environmental and social protections from planning through post-closure. Environmental impact assessments (EIAs) at early stages. Stakeholder mapping and community consultation. Continuous monitoring of air, water, and seismic activity. Transparent public reporting. Emergency response and remediation plans. Case studies on social impact. Sleipner, Norway. Offshore project with minimal public opposition. Transparent data sharing and safety record have built international confidence. Barendrecht, Netherlands. Onshore project cancelled after public resistance, despite scientific approval. Demonstrated the importance of early and inclusive public engagement. Illinois Basin Decatur Project, USA. Strong community support due to outreach, education, and job creation. Emphasized community partnership and university involvement. Environmental monitoring technologies. Advances in technology help ensure safety and transparency. Seismic imaging and microseismic arrays to track CO underground. Soil gas and groundwater sensors for leakage detection. Fiber optic cables for real-time data. Satellites and drones for surface monitoring. AI and machine learning to predict and manage risk. Ethical and intergenerational concerns. CCS raises long-term ethical questions. Stewardship. Who is responsible for CO centuries into the future? Risk transfer. Is CCS delaying more permanent climate solutions? Moral hazard. Will CCS reduce pressure to phase out fossil fuels? These concerns demand transparent debate, robust governance, and integration of CCS with broader decarbonization efforts, not as a substitute but as a complement. Moving toward responsible CCS deployment. A socially responsible and environmentally sound CCS strategy requires integrated planning, aligning CCS with energy, climate, and community goals. Inclusive decision-making, giving communities a voice and stake in CCS development. Transparency and accountability, public access to project data and performance. Long-term monitoring and stewardship, ensuring intergenerational responsibility. Part 10. CCS in the context of net zero and the energy transition. The global net zero imperative. The goal of achieving net zero greenhouse gas emissions by mid-century is now central to global climate strategies. Over 140 countries have committed to net zero targets, covering more than 90% of global GDP. In this context, carbon capture and storage (CCS) is increasingly recognized as a necessary enabler of deep decarbonization, especially for sectors where emissions are hardest to eliminate. The role of CCS in decarbonization pathways. According to leading organizations such as the Intergovernmental Panel on Climate Change (IPCC) and the International Energy Agency (IEA), CCS is essential in three main areas. 1. Decarbonizing hard-to-abate sectors. Cement, steel, chemicals, and refining cannot be fully electrified. CCS enables low-carbon operation without dismantling core industrial processes. 2. Low-carbon power and hydrogen. CCS allows natural gas and coal plants to operate with reduced emissions. CCS is a key enabler of blue hydrogen, which is produced from natural gas with CO capture. 3. Delivering negative emissions. Bioenergy with CCS (BECCS) and direct air capture with CCS (DACS) are critical for removing CO from the atmosphere. Net zero scenarios require gigaton-scale CO removal to balance residual emissions. Integration with renewable energy systems. Although renewables like wind and solar are the backbone of the low-carbon energy transition, CCS plays a complementary role. Provides dispatchable, low-carbon electricity to balance intermittent renewables. Enables low-carbon fuels for sectors like aviation and shipping. Offers CO management infrastructure that can be shared across industrial clusters. CCS is not in competition with renewables, but rather a bridging and balancing solution that fills critical decarbonization gaps. Regional deployment outlook. The future of CCS will look different across regions. North America. Strong potential due to vast storage resources, industrial base and policy incentives, e.g. 45Q. Emerging CCS hubs in Texas, Louisiana, Alberta and Illinois. Europe. Focus on industrial decarbonization and shared CO infrastructure, e.g. the Northern Lights project. Cross-border cooperation, enabled by EU policy frameworks. Asia. Significant potential in China, Japan and South Korea, especially for hydrogen and industrial emissions. Emerging projects and growing policy support. Global South. CCS may play a smaller role initially, but could expand with international support and financing, especially in high-emitting industrial zones. CCS infrastructure of the future. To support net zero goals, countries must invest in CO infrastructure at scale, including capture facilities at power plants and factories, pipeline networks and shipping terminals for CO transport, regional CO storage hubs with shared injection sites, digital platforms for monitoring, reporting, and verification. This resembles the oil and gas industry's infrastructure but in reverse, moving CO from source to sink instead of fuel from well to burner. Key enablers for scaling CCS. Several systemic factors will determine the success of CCS in the energy transition. Stable carbon pricing to reward emissions reductions. Blending CCS with green hydrogen, renewables and circular economy models. International cooperation on standards, finance and knowledge sharing. Financing mechanisms that reduce upfront risks and attract private capital. Public acceptance, driven by transparent governance and equitable project planning. Avoiding the pitfalls. Despite its potential, CCS must avoid becoming a distraction or excuse for delaying the broader energy transition. It should not be used to extend the life of high-emission fossil fuel projects without real emissions reduction. Replace necessary investments in renewables or energy efficiency. Undermine efforts toward a just and inclusive energy system. CCS is not a silver bullet, but one tool among many in a diversified climate strategy. Looking ahead, CCS in 2030, 2040 and beyond. The next 5 to 10 years are critical. Without accelerated deployment and investment, CCS will not meet its potential in time to help stabilize global temperatures. Final thoughts. In the era of climate emergency, CCS represents both technological promise and moral responsibility. It must be deployed rapidly to meet the pace of the climate crisis, fairly to ensure it serves all communities and nations, responsibly, with full transparency, oversight and integration into sustainable energy systems. If done right, CCS can be a pillar of the clean energy future, locking away emissions and buying time for the planet's transition to true sustainability.